Now, in a previous video, we looked at a bunch of examples for intrinsically linear models. So you could see the full range of how we do that analysis for the different types of transformations. Now, these are, of course, not the only possible transformations that you can do. You can perform square root transformations. You can get a square root model out of that. So, I mean, you should not limit yourself to only these. Think of these transformations of X or Y as ways, just sort of generally, to transform your variables. Again, sometimes because we're trying to fix problems like non-constant variance in our residuals, but typically it's because we just get better fits, or because we're expecting the outcome to be a particular way. Maybe we're expecting to have a square root outcome. And so we want to get it to fit to that kind of a model a little more effectively. So think of these types of transformations sort of in broad terms. Now, what I want to do in this particular case is, because that was like a lot going on in that other video, what I want to do here is just do one example to kind of make it a little bit more compact. This is an exponential example because those are somewhat common. And then what we can do then is we can also think about there's another video that I've already posted a couple of years ago that's also in this playlist on COVID that also discusses the exponential model. This is going to be a little bit more statistically rigorous because we're going to use the data analysis toolpack in our analysis. The other one mostly just went with the graphing approach using the scatter plot. But it's another example, and this is real world data in the COVID video rather than this is simulated data in this one. All right, so imagine you're investing money in the stock market. You put in some money, let's say $10,000 to start with, and then every year you earn interest on that money in the stock market. The stock market tends to grow at around 10% per year, but the rate is a little bit variable. Some years there are boom years, some years there are recession years, you earn more or you earn less. And there's some variability in how much money you make each year. And so this data is simulating that sort of variability. It's the variability in the interest rate tends to, again, be mostly normally distributed. I used something that was a little bit easier to set up, which is a little bit more uniform. But it still had, there was some randomness to it. There was some variability. And but we still, in the end, what we see is approximately exponential growth. Each year, we add on, we take the previous value and we add on a little bit more, and then that becomes the input into the next year, and so on. And so I've just used a ran between function between 7 and 13. So that's our random interest rate. And then every year, again, we just take the previous year's value, and we find a new interest rate and we calculate it, and as it keeps going. So what we're going to do is we're going to create and plot this data into our scatter plot, and we can see that it is curved. And again, because these are all sequential, the graph is trying to create a line graph from the data, and we don't really want a line graph. And then I'm going to add our axis titles. Year of investment. And amount in. All right, so here's our graph. We can see this isn't a straight line. You could choose exponential from the graph, but I want other options, so I'm also going to do it from here. And I'll leave the trend line, the straight trend line on there just for comparison. And I'll put my equation on the graph. Grab the wrong thing. Move it out of the way. Now, one thing to kind of keep in mind, you can see from our power here, it's very hard to see because it prints very small on the scatter plot, but that is around 10% as an average, which is what you'd expect from this data. And this is supposing that we started with only 9185, but that's year 0. And we started counting in year 1, so that's fine. There is some variability in our data. It's not perfectly smooth exponential, but we do have a pretty high R-squared value. All right, now, as we saw in the last video, if we want to, in the intrinsically linear video, if we want to do sort of more analysis beyond what we have here, we have to perform some transformations on our data. And so for that, I am going to copy and paste this data. And I'm going to paste it as values so that it stops updating with the graph every single time. Just so that as we do our transformations, it's not constantly also updating. All right, so what we're going to do is the exponential model. What we want to do to make it linear is we're going to need to take the log of the y values. So we're going to call this lny. And that's going, and notice this will update every time I hit enter, and you can mostly ignore it. Log of y is going to be ln of that. And just to kind of be aware, it is okay to use the log to like log base 10 or some other base. If the math, the coefficients and everything will come out slightly differently, but the math is basically going to work the same. Change of base just means that there's a constant change. It's not a big deal. It's a scaling factor. Okay, and so now what we're going to do, again, just so that we have it, we're going to create our our scatter plot of the transformed variables. There we go. And impose our trend line. Now, again, the original data is constantly updating. As we have the transformed data, we can then calculate things like our slope and our intercept and the correlation, the linear correlation, using the built-in formulas, using the transformed variables. Again, that matches the slope coefficient on our graph. We can calculate the intercept. Again, order here for these matters. The y has to go first for those two. One sort of way to verify that everything is working properly is to do it both ways so that you can see. Again, the issue is that when you're plotting these, they have to be in left-right order, x on the left, y on the right. If not, it'll switch the variables and you might catch that mistake when you're doing these calculations, and the correlation doesn't care about the order. But we'll keep it the same, I guess, this time. And again, that if I square that, then that will give me this value. Squaring numbers less than 1 will make them a little bit smaller. All right, and so now what we then want to look at again is that data analysis tool pack so that we can do our additional diagnostics. And so data. The Y values are not all the way over there. That's where they were before in the last video. Again, make sure that you're starting if you're using the labels, that you have the labels box checked. If you're not using the labels, make sure you don't check the labels box. Where do we want this output to go? I don't want it to go all the way over there. Let's just put it over here. And we'll check our residuals. And let's put in a 80% confidence level. That's an interesting residual plot. Normally you shouldn't get a residual plot that looks like that. That's a bad sign. Oh, I had my, I have to redo this. I had my constant equals 0 checked from last time. I don't want to change anything except to turn the constant back on. Let's overwrite everything. That's good. All right. There we go. That looks better. All right, so that actually doesn't look that bad in terms of, I mean, there's no clear pattern, and the variance actually doesn't look too bad, so that's a good sign. Let's look at our coefficients. Those match our graphs. That's great. Let's do some hypothesis testing. Our model, there's definitely something going on in our model that we like. That's much less than 0.05. If we look at our two coefficients, both the intercept p-value and the slope coefficient p-value are less than 0.05, so that's good. Again, remember, these e's mean that's zeros and then the number after the decimal place. And if we look at our confidence interval bounds, our intercept has a value between these two values, and our slope coefficient is between these two values. And again, they really close to 10%, which is, again, what we would expect. The 80% confidence intervals, again, they're narrower than the 95% confidence intervals. We're trying to capture less of the data, but again, they're centered at the same places as our coefficients. So that's excellent. That worked out really well.